Hey everybody! This next part is about chapter 2, which is focused all on the method of science. So there's probably a few things in here that will be a review for a lot of you, and some of it will probably be new information that you may not be familiar with. So I do encourage you, if you're confused about any of this, to read through this chapter in the textbook. And if you have any further questions, by all means, email me or come by and see me. So what is science? Most of you probably have a general idea about what science is. So it's basically a process for producing knowledge methodically and logically. It typically depends on making precise observations of natural phenomena. So we're going to measure something and record the data and look at different factors that affect those measurements and what's going on in natural systems. Science is also a cumulative body of knowledge produced by many scientists. And it's a way for us to explain how the natural world works and meet practical needs. So there's basic science where we're just trying to understand what's going on, and there might be other types of science where we want to know how we can apply it. So applied science, like in forestry, often we might be having different treatments on our forests to see which ones make our trees grow straighter for better timber, or grow more quickly so that we can produce more wood in a shorter amount of time. So that would be more practical. There are a number of principles of science. So one is empiricism. This is that we can learn about the world with careful observation of empirical, so real things going on outside. So I can, estimate the number of squirrels in an acre, and that would be an empirical phenomena. And we can also use this information to understand fundamental processes and natural laws. Uniformitarianism is basic processes and patterns are uniform across time and space. So things like understanding gravity and how atoms work, we know that those are things that aren't changing over time. Parsimony is a really important one, so I'm going to want you to remember this one. This is when there are two plausible explanations that are reasonable. The simpler one is generally preferable. In general, we want simpler models because they're easier to understand, and it's much more likely that the simpler answer is the actual answer. This is also known as Occam's razor, which you can see listed right here, after the English philosopher who proposed it. And so we use this a lot when we make a bunch of models to understand what's going on with wildlife populations, for example. I might have a really complicated model, and it's just as good at predicting the data for the wildlife population as a simpler model. And so we prefer the simpler model because it's just much more likely that the simpler explanation is what actually is going on. Uncertainty. It's important to know that scientific information changes over time as new evidence appears. So as we collect more and more data, we understand things better. So it is possible that we're not measuring something that we didn't know we needed to measure, or we didn't have the technology to measure it very accurately, and that might change how we understand how processes work or what's going on. Repeatability means that tests and experiments should be repeatable. If the same results cannot be reproduced, so if you do the same experiment multiple times, you should get the same answer. If you don't get the same answer, then the conclusions are incorrect, or there's some other variable affecting the results that you did not take into account. So that can be important. Proof is elusive. In general, scientists don't say that they proved something. That is something I see a lot actually in undergraduate papers where like, we proved this. No, proving something is really difficult. You need a lot of evidence that all goes in the same direction. and it needs to be tested many, many, many times. So we rarely expect science to provide absolute proof of something, that like a theory is correct, because new evidence can always give us a different understanding, or kind of question what we thought we knew. So proof, not something we normally talk about a lot. Another principle of science is testable questions. So to test whether a theory is correct or not, it must be tested. So we must come up with these testable statements to see if it behaves in the way that we predict that it does. Science also depends on skepticism and accuracy. So scientists ideally are skeptical and unbiased. And what we mean is healthy skepticism. So every time there's a surprising result, we want to be skeptical about it, which means we want to look into how was that result created? Is there any other thing that we didn't measure that might have affected it? Or might there be an effect of our treatment that's different than we intended? And there's a lot of things like that. So some examples are, there have been some studies to look at whether excluding predators affects the populations of prey. And sometimes they would do these fenced in areas where they kept the predators out, or at least they thought they did, and then they found out later that there were like birds of prey that like to perch on the posts of the fence. And so they didn't have the same treatment. They were trying to keep out ground predators like snakes and some other things, and raccoons, but because they put these posts up, they were a great place for birds to sit and then maybe pick off the small mammals that are in the enclosure. So sometimes our what we think we're testing is different. So it's important to be skeptical, because sometimes we design experiments or don't take something into consideration that we should have, and that's why we're always questioning those results and looking at it in an analytical way. So we're not just saying that that's not plausible and making up some other theory. We have to have some reason, some logical way of coming through to the conclusion that this may not be correct. So that's what healthy skepticism is. It's important to note that some people come up with these conspiracy theories, and if you remember, that's usually not very parsimonious. Conspiracy theories are usually very complicated, and so by parsimony, a lot of times we would want to reject them. But it's just important to note that healthy skepticism and conspiracy theories are like totally on different ends of this spectrum. Scientists also strive for accuracy, so we want to check our measurements. We want to calibrate our instruments. We want to check to make sure we're measuring things in a way that are working properly. So you might not worry about that if you're using a ruler. Like, your ruler is probably correct. But if you're getting down to really tiny, tiny measurements, different people might interpret what's on the ruler slightly differently, and that could cause some variability in the measurements. If you're using an instrument, you want to just be able to check that it's working properly, and you want to build things in to make sure that measurements are accurate, so that you feel that your data is reliable. And again, coming back to reproducibility, well, I want to be able to repeat these results. So if I did the experiment this year and then I did it again next year, I should get the same results. Or if I do an experiment and somebody does exactly the same experiment in their lab in California, we should get the same results. Now, we might have slightly different room temperatures or slightly different compounds in our air quality or something like that. But if that's not something that affects the process we're measuring, that shouldn't matter. We should still get the same general patterns. Also, repeating things is often called replicating them, or replication. We also have replication within experiments, because if you do it to just one area, maybe there's something strange about that one area that makes it respond differently than other areas. So you want to do it in multiple different places and have it be replicated so that you have confidence in your results. So this is the general scientific process, which probably most of you learned in school. So you identify a question, you form these testable hypotheses, collect data to test the hypothesis, and then you interpret results. It is always important to consult prior knowledge when you do the identify the question and the interpret results. So that means you go in and you read as many past scientific papers as you can to understand what other people have found related to what you're studying. And it's important to look at prior knowledge when you're interpreting your results too, because maybe somebody has some insight that will help you understand what's going on in your experiment if you got results that you did not expect. If you reject your hypothesis, you need to come up with a new one and start over. And so this is how we figure out how natural processes actually work. Once we have results that we want to report, we write them up as scientific papers. We may give a talk at a scientific meeting first to discuss it with other people. And peer review is when other people, other scientists read through your paper and they tell you everything that might be wrong with it, basically. And then you have to address those comments before it's actually published. We'll talk more about that in a minute.